In real circuits, voltage and current do not always change instantly. When a resistor and capacitor are combined, the circuit begins to respond over time instead of immediately. In this lesson, we will learn RC circuits and how they create fundamental time-dependent behavior used in almost every electronic and RF system. An RC circuit is an electrical network composed of a resistor and a capacitor connected together, typically in series or parallel configuration. This simple combination creates one of the most important time-dependent behaviors in circuit theory. Unlike purely resistive circuits, RC circuits do not respond instantly to changes in voltage or current, but instead evolve over time. The presence of the capacitor introduces energy storage into the system, while the resistor controls the rate at which energy is transferred. This interaction between energy storage and energy dissipation defines the dynamic behavior of the circuit. As a result, the circuit exhibits gradual charging and discharging instead of abrupt transitions. RC circuits form the foundation of transient analysis in circuit theory. They are used to model how signals evolve over time in real systems, making them essential for understanding filters, timing circuits, and signal processing behavior in both analog and digital electronics. When a voltage is applied to an RC circuit, the capacitor begins to charge through the resistor. At the initial moment, the capacitor behaves almost like a short circuit because its voltage is zero. As charge accumulates, the voltage across the capacitor increases gradually, while the charging current decreases over time. This process follows an exponential behavior governed by the time constant tau, defined as the product of resistance and capacitance. The time constant determines how quickly the capacitor charges or discharges. After about 5 time constants, the circuit is considered to be effectively in steady state, where the capacitor is nearly fully charged. When the input voltage is removed, the capacitor discharges through the resistor. The stored energy is released back into the circuit in a controlled exponential decay. This predictable behavior is fundamental to timing and waveform shaping in electronic systems. The time constant in an RC circuit represents how quickly the system responds to changes. A large resistance slows down the charging process, while a large capacitance increases the amount of energy that must be stored, also slowing the response. Together, they define the overall speed of the circuit's dynamic behavior. From a physical perspective, the resistor controls how quickly charge can flow, while the capacitor determines how much charge must be stored to reach a given voltage. This interaction creates a natural delay between input and output, which is essential in many signal processing applications. RC circuits are often used as simple models for more complex dynamic systems because their exponential response captures the fundamental behavior of many physical processes. This makes them one of the most important building blocks in circuit theory. In practical engineering, RC circuits are widely used in filtering, timing, and signal conditioning. Low-pass filters allow low-frequency signals to pass while attenuating high-frequency noise, while high-pass filters do the opposite. Both are built using simple resistor-capacitor combinations. RC networks are also used in timing circuits, where controlled delays are required. Applications include oscillators, pulse shaping, and digital signal conditioning. The predictable exponential behavior allows engineers to design precise timing responses without complex control systems. In real-world electronics, almost every system contains RC effects, even if not explicitly designed. Parasitic capacitance and resistance influence high-speed circuits, making RC analysis essential for both low-frequency and high-frequency engineering. In RF engineering, RC circuits play a crucial role in shaping signal bandwidth and frequency response. The frequency-dependent impedance of capacitors combined with resistors allows engineers to design filters that control which frequency components are transmitted or blocked. RC time constants also define the cutoff frequency of many RF and communication circuits. This determines how fast a circuit can respond to changes in signal, which directly affects bandwidth and signal integrity in communication systems. Understanding RC circuits is essential for RF engineers because they form the first step toward more complex RLC and distributed systems. Many real RF behaviors originate from simple RC interactions at the component level. In this lesson, we learned that RC circuits combine resistors and capacitors to create time-dependent behavior based on exponential charging and discharging. This behavior is defined by the time constant and is fundamental to filtering, timing, and signal shaping in electronic systems. In the next lesson, we will explore RL circuits and compare how inductors introduce time-dependent behavior through magnetic energy storage. If you found this useful, like the video, subscribe, and follow for the next lesson.